to the final day of the workshop with a talk by John about quantum information.
Thank you. All right, so good morning. So I will start with, at the place where I finished yesterday. Maybe let me say that I have uploaded some notes on the site, on the website of the Newton Institute, in the kind of the workshop page. So they are by the end of the program I hope to have full notes for everything. Now it's about maybe it's in some sense it gets more, in some other sense it gets less. So at the moment, right? Some of these lectures are covered in more detail, some of them in less. That's it. But yeah. Right, so recall now that from yesterday that given, so these are just finite sets that will be the input and the output pairs. And if I just take a look at X and A, I associated with that the sister algebra, which is generated as a sister algebra by elements EXA, X from capital X, A from capital A, which are orthogonal projections. And they are PVMs over A for every X. And now I'm considering the maximal tensor product of these two, Alice's side and Bob's side. And over here, let me call this capital A for this part, the MPA hierarchy that I want to kind of do. And then over here, a word is just, so these are the generators, G, let's say G are the generators, all EXAs and all FYBs. And then G sub K, let's say, will be the words of length K on those generators. So this is a word on G of length, at most K, not K, right, at most K. Right, and the polynomials are just of degree at most K, are just the span of these words, and everything I view inside the sister algebra A. But it somehow loses, when you go at this level, it loses the sister algebraic kind of flavor at all. It's just a linear thing. You have some kind of, it's a linear space, really, right? And then I kind of single out only those linear functions on A. So remember, I want to see when if I'm given a linear function on A, is it a state on A? This was linked to the QC correlations, right? Via the characterization theorem that I mentioned.
One question: so do you take just words, or do you take the span of words?
G sub K will be just the words, and then and then let me take. All right, so let me take the span polynomials for P sub K, right? So these are just polynomials then. So capital P, let's say, to distinguish from the correlations of degree at most K, and in other words, this is just the span, the linear span of G sub K. Yeah.
That's an operator system, right?
Very good, exactly. So this very nice, exactly. It's an operator system. That's what's lying behind the MPA hierarchy. In fact, indeed, it's about operator system structures that approach the cons of the full sister algebra. Exactly. And exactly in these kind of operator systems, as we know, there is this order unit that you need to have. And this is at the heart of MPA hierarchy, at least the way I see it, that you do have order unit for these operator systems with their kind of algebraically generated cons. So yeah, so in more detail, slightly more detail, let's see now.
So it's a finite dimensional.
Yes, correct. It's a finite dimensional operator system. Yes, correct. Right. So let me single out the functionals on A. And maybe let me give a notation also for the span of all those, which is a dense subspace of A. A sub 0, this is the union of all those. So C-star dense set inside space inside A, the star algebra. Right, so let me single now S sub k to be those functionals on A0. I will always assume unital, so this will be unital. So S of 1 is 1. But I do not insist on positivity everywhere. I just insist on positivity only on the squares or sums of squares that will be equivalent of polynomials of degree at most k. So my constraint here will be this functional applied to some polynomial p start p is non-negative if degree of p is at most k. So I have jumped operator system, yes, but actually these are not the right operator system that I want. I want the 2k levels because I want to have a positivity structure on the 2k levels. I have multiplied p start by p, so it's 2k. Right, so these are some functionals on A0. And now it's just a straightforward thing to see. It's really a one-line thing to see that if you take a so if I evaluate S just on words now, let's say beta start alpha. So these are just words. I have passed from polynomials to words now, just on words. These are of length at most k. So this one-line kind of calculation, literally one line, shows that such a matrix will be positive semi-definite precisely when my S is positive on the p star p polynomials. I just analyze the polynomial sums. Right. So fine. So very well. So now the next thing is that, and this is the crucial bit for the MPA hierarchy as I see it. Is that if you have something, if you have a functional that is positive, that is in all of those S sub k's, so it's algebraically positive, let's say, there is no C star conditions there. In fact, it automatically extends to a state on A. And that's exactly the point where it's not necessarily true all the time. Anytime you have some star kind of dense subalgebra. So this is the kind of lemma that I can, given some S that is in the intersections of all those Sk, there exists a state, some kind of yes, extension if you wish, right? On the whole A, which restricts to S. So for this, you try to do GNS construction, right? But the problem is that if you try to write down your inner product, it's fine. But what the problem is with the boundness of the elements, right? And over there, what you see that you need is some kind of order boundness. You want, if you have, so the main kind of element here of the proof is that such an S that is positive semi-definite, it's positive on all those algebraically generated cons, has the property that if I have a word on G, and if I have some element S in here, then if I estimate S on W, well, it is non-negative, but I mean, the more important thing is it is always bounded by what? Well, it's non-negative, yes? Yeah. Yeah. Let me write like that. It's not necessarily non-negative, it needs to be symmetric, W to be non-negative, yes?
So for A0 to sit inside of A, are you like collapsing all the tensor factors onto each side?
Right, right, yes, exactly, exactly. I'm using, yeah, I should have mentioned that these are reduced words. So the first come the e's and afterwards come the f's. I can reduce them because I do them. It's an algebraic property. It's nothing again to C star or anything. You just have this condition of commutation, right? Yeah. All right, so let's see now. If you have a symmetric word, this will follow if I know that it's true for symmetric word just by a simple kind of 2 by 2 matrix argument. And why is it true for symmetric words? Well, why is it true for a word, just a very simple word, the generator? So this is really the question, the first question. So if I have any generator, say E, right? E is either the E's or the F's, or G, G. So G is a generator. Why is this thing between 0 and 1? Well, because it is G itself. So if I take a look at 1 minus G itself is a sum of squares, right? Remember the relations, so G is one of those E's, so there are a few more of them that add up to 1. Each one of them is a self-adjoint, it's an orthogonal projection. So let me write it like that. E minus EXA, 1 minus EXA is the sum of EXA prime, where A prime is not equal to A. And these are squares. These are E star P. So this one is then positive in that case, right? So S satisfies positivity on those, so therefore it satisfies positivity here, and you have the boundless decimals. So then afterwards you just do induction, right, on the length, right? And you have something in the middle, you split it. Right, so this allows you to do your GNS construction, and fine, you have this kind of observation. And then what is the actual hierarchy? So I will define now the actual correlations of some kind of level, on some level K. This will be the following. I will take an element of my S sub K set, and I will just restrict to the first entries. So a correlation should look like that. It should have only those entries, X, Y, and A, B. And some of them may come from some S evaluated at EXA FYB. And here I can choose S to be only from the set S sub K. So I'm taking all these metrics, I'm taking the matrix that I had here, and I'm restricting it only to the entries alpha and beta being equal to these ones. And this is my kth level of correlations. So S sub K, I think yesterday I wrote like that, will be just the set of all those. Let's call this P sub S here. This will be just P sub S, where S comes from S sub K, capital S sub K. And now the NPA hierarchy says that, so this is the theorem of Navasquez, Peronio, and Athin. It's saying that if I take the intersection of all those over all K, I obtain the class of QC correlations. One inclusion is trivial. Of course, if you have a QC correlation, it's in all those classes, right? You have a state on the whole sister algebra, so positive on the graded polynomials. So the converse is, so this is again a sketch of the proof. The idea here, if you start with some P in the intersection here, this means that for every single K, this P will come from some P s little s K, where little s K, it belongs to capital S K. Now I want to see, so that's true for every K you have a different one here, and I want to represent it as a single one. But then this again boils down to the same boundless condition here. You can apply kind of successive kind of choosing kind of compactness arguments, really, right? Choosing successive sequences, subsequences of these SKs, which converge on a larger and larger words of a larger and larger length. And for this, I need the boundless on the words again. So this condition over here. Right? So I'm not writing down all details. The thing is that it's the same again the same lemma. Well, not really the lemma, but the sublemma. this one here really, that shows you that you can choose a convergent subsequence. So this S sub k will converge, a sequence of those will converge to some S, which S will have positivity property on every polynomial of the form P star P for finite degree P. But this is, by the previous lemma here, this is just a restriction of some state on the whole A. And we know that these ones, so this S first is positive, it belongs to the intersection of all SKs, first of all. And a posteriori, from the lemma, it is a restriction of a state on A. So S comes from some state on this encoding maximal tensor product of the game, of the correlations rather. Right, and therefore it belongs from the previous observation, it belongs to QC.
So these CQCK, do they have any physical interpretation or?
CQ, yes. Right, no, so physical interpretation I don't think so, but I'm not aware. But what they have is kind of easily to verify. So it's easy to verify simply because you have some linear constraints every time for your, of course this, if you start with an arbitrary functional on the tensor product, it's easy to verify. Actually it's enough just to say, to take the tensor product of these operator systems on two sides, so finite dimensional thing, it is by this observation here, it's verifiable whether it belongs to my set S sub k. Positive semi-definite kind of a condition. Right. So it's a kind of a completion, positive completion of matrices problem. It becomes, right? So you start with something that is in general a correlation. You're asking, is it here? Is it in this set? And what you need to verify, of course, what you know is only the ground level, A, B, X, Y. So now what you are asked to verify is whether this kind of bunch of scalars can be put in kind of into this one entry, one entry of matrix that's positive semi-definite for every k. But for every fixed k, this is verifiable, right? This is kind of a problem that has been kind of, of course, studied and imported and so on in various aspects of optimization, right? When a matrix has a positive completion. So for every fixed k, you can verify it kind of efficiently, let's say, whatever that means. And then you can, if it's not in SK for 1k, then you know that it's not in here. Right? So kind of finite time, in a sense, it spits out the answer that it's not in there. All right, so now what is this good for? So let's go to values of gains. So recall that, again, that if I'm given a certain certain type of correlation, certain type of resource, QC in that case, and if I'm given a game, lambda sub pi, lambda comma pi, this kind of non-local game, this has an optimal winning probability when you play with this particular correlations QC. Now this will be, I can define in that case k versions of this. And the k versions will be the same thing as before, supremum of the omega of lambda pi comma little p, where little p belongs to C QCK. And now this intersection property gives me that the QC value will be the limit. So I should say, so it's a limit from, yeah? Exactly, it's a limit from below, so they're decreasing. They're strictly decreasing these values. So it will be the limit and it will be the in. They're decreasing, it's a decreasing sigma, so it is the limit of omega QC k of lambda pi, which is also the infimum of over k of omega k QC lambda pi. Yes, of course. Where? Here? No, where? Where do you want? Yeah. Right. All right. Fine. So now, if we go back to MIP star equal RE, at the heart of, well, not at the heart, there's many hearts, I guess, right? Many different kind of highlights, obviously, in this paper. But one of the things, one of the ideas there is that you have, so going back to Sergei's talk, you really want to see whether the QA value is the same as the QC value, or rather you want to distinguish them. Both of them are not easily computable, not easily verifiable, not easily kind of, you cannot easily arrive at them. This is kind of uses infinite dimensional Hilbert spaces. This one uses finite dimensional, but kind of arbitrary dimension, higher and higher. So what they do, so let me write it actually here in the middle because I want to extend it. So this is the question here. And here you have this kind of, this is the one, so I need to write it the other way around, right? So they are decreasing. And here, you can have a similar thing just by restricting the dimension of the Hilbert space where these tensor models live. So you will have a similar sequence approximating the QA value, but from below. So you will have one-dimensional ones here, right, Q. Then you will have two-dimensional ones, Q, and so on. So, yeah.
Is it quite obvious that if the values of QA and QC equal, is that the same as the collections of correlations?
So what we can definitely do is that if they are not equal, so this is the question. So you're aiming for not equality, inequality. So if they are not equal, you know that the correlations are not. Yeah. Right. So this kind of this kind of hierarchy is coming from both sides approaching these two values. Is one of the things that is used in the paper MIP star equals RE. Right. So the advantage here is that all these before QA and all these here, they are good for computation. Right? They're good for computation. They have, yeah, they are amenable to complexity theory to computations, verifiability. All right, fine. So then this is the end of the second lecture. Right. So I have another 45 minutes. It's 2 slots of 45, right? At the moment, right? Yeah. Okay.
There was another QS.
Sorry?
There was another class of
Right.
class, so that will be important.
So QS will be the QS value will be the same as the QA value and the same as Q. So this is usually just written Q, because if you're taking supremum, it doesn't matter. So the dimension can be arbitrarily large, but if you play with infinite dimensional Hilbert spaces, as long as they're in a split form, this you can approximate with finite dimensions, this also with finite dimensions, so you have the same closure. So the QS set will have the same closure as the Q set. Yeah.
So one clarification. So in all this setup, you are considering the tensor product, right?
Correct. Yes, yeah, the tensor product you do not. For all these things, you do not need any completion, right? You do not need any completion here. You just have the algebraic tensor product. Everything is just purely algebraic.
Okay, so if they are in the state when you are evaluating, you are just using tensor.
Which part? Here?
In the differential piece.
Correct, yes. So over here, I'm just taking some functional that is positive on these factor polynomials, and
I think we've identified EXA with EXA tensor 1.
And FYP with 1 tensor.
I didn't understand it. Again. So what is the
Whenever
solution?
you're writing EXA, you really mean EXA tensor 1, I guess.
Or you agree that this is the
The question was whether in this.
Yeah, okay, I understand. Yeah. Yes, yeah. So EXA sits inside here. It's even in the algebraic tensor product, right? I see it inside A. I see them, these two copies, these two sister algebras. I see them inside the algebraic tensor product, right? It's some kind of commuting
So if I consider say the free product of those two algebras,
This, yes.
and abelianize the two product.
Yes, it will be the maximal. Well, that's a fancy way to view the maximal tensor product. Sure, of course. Yeah. Yeah.
You might want to mention the group algebras 3.2. This is the free product of n copies of CK. And then what that tensor is that's the group C star algebra. When you do the group cross group, and that A0 was just the C algebra.
Right. Okay, so this one here, each one of them, that was mentioned in Sergei's lectures. This one is a group sister algebra of the free product of these cyclic groups x times, and then you have maximal tensor product with another group sister algebra, so it becomes then the product of the two groups. So it's the group sister algebra of the product of this free product group with this one. This will be y of them. This A sub 0 is just the group ring or group algebra of this sister algebra of this group. All right. So then the next. So I will make a break. Right. So maybe shall we have a break now for 2 minutes and then continue, because it's just the natural place to stop. Yeah. Shall we start, maybe? Okay, thank you. So the next aim is first some examples. This will lead to a link to the quantum permutation group that was presented by Mike in the first lectures, and then Mateus has discussed this. So kind of links with quantum permutation group. Graph isomorphisms, classical graph isomorphisms. We will see that the algebraic or quantum group route to quantum graph isomorphisms has an operational interpretation in terms of non-local games, winning strategies of non-local games. And afterwards I want to quantize graphs. I want to kind of have a kind of first kind of view on what a quantum graph is or should be or can be, or maybe. Right. All right, so one of the first starting point maybe of these kind of interactions between operator algebra representations, states on sister algebras, and non-local games arose from the coloring game. So the graph coloring game, it was early on, probably 2005 or something, a paper by Cameron, Winter, et al. So there's Severini, several more people. And the game is, so it's a non-local game. The game is you start with a graph G, and you start with some number K. So this is an integer number. You're trying, so in that case, the two players are trying to convince the referee that they possess, or the verifier, that they possess a coloring of the graph. And the coloring, remember, a proper coloring is an assignment of colors to vertices so that adjacent vertices have distinct colors. And the graphs here are just simple, no loops, no repeated edges. So here is a vertex, and here is a vertex, color, back color. And then, the kind of the conditions are that if we have two adjacent vertices, then the corresponding colors have to be distinct. And that's not enough, because this kind of game is trivially winnable. In order for the verifier really to be convinced that the players possess a coloring, you want that if the two vertices are the same, the colors are also the same. The colors they respond with are the same. So this was the first kind of, one of the first non-local games that linked to quantum information theory. In fact, non-local games have been studied way before the advent of quantum information theory in theoretical computer science, using just classical strategies. And this author showed that you can compute then a quantum chromatic number of the graph, the smallest k for which you can win this game. And they show that for some graphs you can actually have strict inequality between the quantum chromatic number and the usual classical chromatic number. And that's a very simple exercise that if you play this game with local strategies, you get exactly the classical chromatic number of the graph. And then one can kind of define other games. One can define, for example, an independence number game where you are trying to fit an independence set in your graph. An independence set is a subset that no two vertices are adjacent in this set. And then you slowly realize something more general. And the first ones to realize it were David and Laura. And they have this very beautiful paper on quantum graph homomorphisms. So you can just talk about homomorphisms. A homomorphism game between two graphs. Coloring game, of course, is a special case because you want to fit G into a complete graph on K vertices. Independent set game is also a special case because you want to have a homomorphism from the complete graph well, not exactly. Here you want the empty graph, right? This will be the click game, let's say, for the graph G. Right. All right. So then, what is the if you put that in framework of non-local games, then what are the corresponding strategy, right? So you notice that you can single out only the second condition, and many games satisfy this condition among other conditions. Right, so we have a perfect strategy for such a game will satisfy the property that if you are given the same input, x is equal to y, then v should be 0 if a is equal, different from b. And you have the following observation so let's call this synchronous correlation. And you have the following observation that a correlation is synchronous if and only if it is presented in the way I wrote. So this is just, perhaps let me write it down in detail. If and only if it has the following representation where tau is a trace now on this, a tracial state. This universal sister algebra. So in other words, for synchronicity, which is kind of intuitively natural, you can get away just with one of the algebras. You do not need the other part at all. And because here kind of the argument is really pretty, after we have the first observation, let me just mention what is the reason behind that. The reason behind that is, so you start with your synchronous strategy and you want to represent it first. You first represent it as some state where S is just a state on the tensor product, on the maximal tensor product. Well, this we know how to do. And then afterwards, what you want to see is you want to extract the trace out of the state using the synchronicity conditions. The state, the trace that you want to extract will be kind of the restriction of the state on the first coordinate. So what makes this work is the following. The synchronicity condition tells you the following, that this state will satisfy the following property. If I have just EXA tensored with 1, XA are fixed. 1 can be analyzed as sums of FYBs, right, for any y, right? And here I should mention that I have assumed implicitly, I haven't really stated explicitly, x is equal to y. The questions and the answers must be the same in order for these games to have any meaning, right? So x is equal to y, and a is equal to b. So you analyze 1 as the sum of EXBs, and you see that the synchronicity condition gives you the following, that you can, the only thing that remains here is E of X A. Yeah, these are the same algebras now, so that's why I was writing E, but maybe it's more clear to write F indeed, yes. So this is just the same, Y is X and A is B, but yeah, this is more clear to write F of X A, and then you can put this on the other side as well. So now you consider, if I consider this element, EXA tensored 1 minus 1 tensored FXA, let me call this H. This is a self-adjoint element. I take the square and I use these relations to show that state evaluated at H squared is 0. That's just algebraic thing. And this afterwards, together with the Cauchy-Schwarz inequality, tells me that I can multiply S on the left or on the right by any element of my sister algebra, U, and I get 0. So let's see now what this means. This means that I can, if I have an EXA here, I can, and something else, this EXA can go to the other side as an F, and then it can go back to the left of U. So this implies that I can commute any word U with words of length 1. And then induction shows that I can commute words of any length. And therefore, I have the threshold property. And the representation is straightforward afterwards. Right, so now if we want to so I should mention that so there is a similar characterization of the synchronous strategies of QA type. Perhaps now is the time for me to say that a lot of those things really, and even if you think about it, kind of the very kind of let's say fact that such meetings with operator algebras and quantum information theory can take these places actually are due to Vern Paulsen, whose insight has been kind of fundamental in this area. So many of those results are actually kind of the ones especially that I will talk about now. For example, the QA correlations did this one as well and so on. So what I want to mention is that there will be a conference, so that's a commercial break. That's a commercial break now, right? A conference in Canada, in Waterloo, in honor of Vern. This will be this summer, end of May, beginning of June. And moreover, this will be the first conference in a series, or a new series of conferences on links between operator algebras and quantum information theory. So yeah, consider coming, consider joining, right? End of the commercial break. So the QA correlations of synchronous type also characterized, of course, by some traces. The corresponding traces that arise are amenable traces. So P is in QA plus synchronous if and only if it is represented in the same way, where tau is an amenable trace, a threshold state. And this was touched upon in Sergei's talk yesterday, and this is really what's at the heart of it. Amenable traces are the one that factor through the minimal tensor product. Corresponding functionals factor through the minimal tensor product. And then it kind of becomes natural that you will have amenable traces representing those. Because the QA class is represented by the minimal tensor product here. All right, so now moving to kind of games where you want to revert. So I want to talk about graph isomorphisms and connection to the quantum permutation group. In that case, you want to kind of be able to revert your correlation, right? So you want, first of all, you want x equals y equals a equals b. And then what you want is to be able to, if you start with a correlation, which we think of something that takes xy and splits out ab, you want to be able somehow to revert this. What is the way to revert it? Well, that's a correlation gives you an information channel, a classical information channel. If you take the dual of the classical information channel, well, our channel is not necessarily a channel anymore. What's lost is the unitality, right? In one direction is trace preserving, in the other direction is unital. So you're naturally kind of restricting yourself now and having unital correlations, right? So these corresponding channels will be unital. Now, if you want to play isomorphism games, then therefore what you would want to have is x equals y as a special case, right? Before going to the graph, before having any graph there, you want to have x equals y precisely when a is equal to b. Not only in one direction, but also in the opposite direction. And this condition on the correlations is the bisynchronicity condition, which adds one more term here, right? In addition to this, you would want, I don't know whether I have color. So you would want P of a given xy also to be 0 if x is different from y. And now, what kind of representation you can have for bisynchronous correlations? Well, let's represent it through a trace of the of my AXA algebra. So now, theorem, if you wish. So I will just formulate for the QC class. P is of QC and bisynchronous, if and only if P arises from a trace where, so this was denoted, what is the right notation? I don't know. So Mike and Mateus will probably tell me what is the right. This was the proof, right? Not the algebra. So the algebra is O usually, right? So this is a tracial state where this was the quantum permutation group described in the very first lectures of the workshop. So remember, this is just sister algebra arising from projections. These are orthogonal projections Pxa with the property that if you take a look at the matrix Pxa, right? So these are projections to start with. The matrix is a bistochastic matrix in the sense that the rows and the columns all add up to 1. So this is a bistochastic operator matrix. Indeed, I mean, if you have such a representation, it's obvious really that you have bisynchronicity by the orthogonality relations of the generators. Why is the opposite true? So if you have, so this is again schedule proof. If you start with synchronous correlation, you know that it arises from a trace. So first of all, you can have a trace on this sister algebra. I'm still writing A and X because although they're the same now, I want to distinguish them, right? Just notationally. So this will represent P, but that's not enough. We want to kind of have a trace on the quantum permutation group. And this property here that your trace can go down to, this is a quotient of AXA by the relations that are missing. The missing relations are the relations P XA over X has to be equal to 1. Then you notice that the bisynchronous condition, the second condition in red, allows you to kind of factor through. Yeah. Going to the QA class, I will just say it, not write down anything. You also have kind of description in terms of amenable traces, and this starts kind of requiring more and more kind of operator algebras perhaps. So it is linked to the local lifting property of free products. So I will not go in there. Right. So now let's go to how is this linked to. So I have until 10:30, right? Until 10:45. Oh, excellent! Very good. All right, that's an unexpected gift. Yeah. So, right, how is this related to graph isomorphisms, quantum graph isomorphisms in the sense of the lectures of Mike and Mateus? In fact, it turns out to be equivalent in that case. So there is a neat equivalence between winning this game and having such a quantum graph isomorphism. So first of all, what is the game, the underlying game? You need to start with two graphs, G and H, on the same vertex set, and you want the conditions. First of all, you want the bisynchronicity conditions. X is equal to y precisely when A is equal to B. And then you want the isomorphism condition. X is adjacent to y if and only if A is adjacent to B. We want to be able to revert these implications. All right. So suppose that you have a winning strategy. So the theorem is if you have a winning strategy for this game. So I'm brushing under the carpet some of the things here. All right. I mean, questions So if you want to formalize this kind of properly, you will see that you do not want, so on this side is really the questions, and on this side the answers. What does it mean if and only if? You have to be able to also ask questions that are vertex of the second graph. So this is what I'm encoding that way, right? Your questions are either vertices of the first or of the second graph. And the answers must satisfy these conditions, right? So these can act as questions as well. Right, so the theorem is that if you have, so this is the graph isomorphism game, let's call it G isomorphic to H. Yeah. Game isomorphic, I don't know, so this is the game. So perfect strategy, if this game has a perfect it's an if and only thing, a perfect QC strategy, if and only if you can find some representation of the quantum permutation group on some Hilbert space. So this will be encoded by some capital P. These will be concrete operators, concrete representation, such that you have the commutation relation that Mike and Mateusz were discussing in their lectures. Remember, there's the adjacency matrix, and they, conveniently for me, they agreed just to write condition like that, ignoring the kind of the tensor term here. So this is the condition that gives you quantum isomorphism of the two graphs in the sense of quantum groups, going through kind of algebraic operator, algebraic fish directly from quantum groups. It turns out that it's the same as this operational interpretation of isomorphisms between the graphs. Now, if you have here, instead of QC local, this is just a scalar metric, it's just ordinary isomorphism between the graphs. So the question that arises, if you have finite dimensional ones here, acting on finite dimensional Hilbert space, you have quantum, you have the Q strategy here. The question that arises is, are these distinguishable? Can you separate these notions? Before that, let me mention just a few words about why this is true. All these operator representations, they serve kind of other means. So kind of this, it's very nice to have, I know, operator representations of strategies, states, and so on. But I mean, are they useful for anything? This is the question, right? At the end of the day, and this one here, the one that I had right there, this theorem, we'll see that actually it boils down to this relation. This is not difficult really to appreciate, right, at all. I mean, it's natural. It's natural to expect that, right? Starting with a perfect strategy, you have a trace on the quantum permutation group. Now take a representation, do the GNS construction on this. Over there you have concrete operators arising from the generators. Faithfulness of the trace then, you remember you're portioning out a huge thing there, so the trace becomes faithful in the image. The kernel you're portioning out, it becomes faithful on the image. The relations inside the trace become proper relations, operator relations, by the faithfulness of the trace. This is what's lying behind it. Right. So, are these distinguishable? This is the next question. So we have kind of a stronger and stronger, or rather weaker and weaker equivalences with isomorphisms of graphs. You can have them just locally, which is the same as classically isomorphic. This implies that they're quantum isomorphic. This implies that they're QC, for example. This implies that they're no signaling. There is also the no signaling isomorphism. This one, very nicely, is in fact the same commutation relation that you see here, but with a scalar bistochastic matrix. What lies there, they're different. So we will see that even these two are different, right? What lies there is the fact that if you have a bistochastic matrix, of course, von Neumann was the precise title of the theorem, right? I mean, it's a convex combination of permutation matrices. Birkhoff, von Neumann-Birkhoff, thank you. Yeah. So Birkhoff von Neumann tells you that it's a convex combination of permutation matrices. However, if you have, in addition, this relation, it's not necessarily true that you can write it as a convex combination of permutation matrices that also satisfy this relation. So you have distinction between these commutations if the graphs are not complete graphs, for example, or empty graphs. Right, so this one is a classical isomorphism. This one here, the NS, is the fractional isomorphism between graphs. And these are not reversible. So this one doesn't revert. And this is again another kind of contained in another kind of beautiful paper of Laura, David, and co-authors. It's a very nice construction involving linear constrained binary linear constraint games, which gives me a chance actually to introduce this sort of games, which are kind of interesting and they can be studied independently of any operator algebraic questions.
So you described somehow how the version of this theorem works for all these correlations apart from Q.
Apart from Q, no, apart from QA. For Q, this will be just acting on finite dimensional Hilbert space.
Okay.
QA, I'm not aware what's happening exactly. I don't know whether that is easily describable. Yeah, Vern? Aha, right. So that's that's one way to see it. Yeah, yeah. So there is something mysterious that Mike and Mateusz would be able to definitely kind of explain. My understanding is the trace. When I formulated this, the trace kind of disappeared here, and my understanding is that the quantum permutation group always admits traces, right? So this is what's lying behind it. For the QA, what you will need to have is exactly as one pointed out, equivalently these ones. It's a representation of the quantum permutation group in a ultra power of the hyperfinite to one factor. In that case, they arise from such a representation. All right. Fine. So then, why is this not reversible? Why can we separate these two? So what's happening there is the kind of the way for one to see it is going to the Mermin-Perez magic square game. So Mermin-Perez magic square game is the following game. You are asked to solve equations. I will give the synchronous version of this game. You are asked to solve equations, so this is a 3x3 square grid. You want to solve here equation, this is a variable. In such a way that for 0 and 1 only, so you're wanting to solve these equations over Z2. If you add the rows, you want to get 0. And if you add the columns, you want to get 1. The sum of every row here is 0. The sum of every column should be 1. So this doesn't have a perfect local strategy, perfect deterministic strategy, but it does have a perfect quantum strategy. So you can win it perfectly using quantum correlations, and the kind of one way to see that is that these, first of all, these relations, I want to make them multiplicative. So I want to talk about the relations of this form x1, x2, x3 equals to the identity up to x1, x4, x7 equals to -1, and so on. They do not have, yes.
Conditions and answers.
Sorry? Say
Can
again?
you tell us what questions and answers are.
Very good. Yes, thank you. Thank you. So, right, very good. So the questions here are, Alice and Bob are given either a, yeah, very good point, thank you. Either a row or a column of this grid, and they want to assign actual values of the variables they are given, either 0 or 1, with these conditions. This they can do very well without a problem, of course, but the trick there is the whole glitch is that they have to agree. The assignments have to agree on the intersection of the variables that they have. So if you wish, one of them is given rows, the other one columns. There are several versions of the game, right? They have to agree. The assignments have to agree on the intersection of the variables, set of variables that they have. For example, if one of them is given a row and the other one is given a column, they have to agree at the intersection of these two. Yes, so these are the rules, and the idea is, why does this game have a perfect strategy? These equations do not have solutions in numbers 0, 1, but they have operator solutions. One can cook up such things using the Pauli matrices, like bipartite tensors of Pauli matrices, this sigma x and sigma z. So one can cook up operator solutions. From there, you can cook up a corresponding PVMs. This will be again symmetries, corresponding PVMs you can cook up that give you a perfect quantum strategy. And now starting from this, one can associate a graph. So that's a beautiful construction that one can, starting with a game like that. So this is a special class of, let me get this right, linear binary constraint system. I think this is the right kind of order in the abbreviation. Games, where you do not need to have just 9 equations, obviously, and you do not need to have just 9 variables. You can have a bunch of equations with being solved over 0 and 1. And you can require some rules, right? Assignment rule is the first one, but in addition, you require some other rules every time. So here there is the rule of agreeing on the intersection, for example. This is the simplest one. The simplest one is agreeing on the intersection of the variables. The assignment has to agree. So given 2 assignments in a LBSC game, one can, so if you're given a question X, okay, question X is just one of the equations here, and an assignment, such kind of tuples will be the vertices of my graph. And 2 of those will be adjacent in the graph associated with the LBCS game, if by definition these 2 assignments disagree on some element in the intersection of the variables participating in these 2 equations. So if F and G are not consistent. So you associate a graph with an LBCS game, and you show that this graph isomorphism game has a perfect Q strategy, for example, precisely when the game itself has a perfect. So this is the graph, right? So this is the graph associated to LBCS game with some constraint vector. So this is a constraint vector, right? The right-hand side is certain constraint vector C for constraint. And then you will have another graph, similarly defined for LBSC of the 0 constraint. You just put 0. This is, of course, trivially kind of winnable. And now the theorem is that these 2 graphs are the corresponding graphs, LBCSC. They are quantum isomorphic, if and only if the game with constraint C has a perfect quantum strategy. This needs work. This is not, so this is in a paper, as I said, by David, Laura, and co-authors. So this needs work, but it is true. So now, that way one can translate the existence of a perfect quantum but not perfect local strategy of the magic square game into an existence of graphs that are quantum isomorphic but not classically isomorphic. The rest of the separations are open. So, of course, this one is open. For example, this one, I'm not sure, I don't think so. No, I don't think this is open. One can look up fractionally isomorphic ones for small graphs. For many graphs, or for some graphs, these will be the same, right? Yeah. But nevertheless, the graphs are not fractionally isomorphic, so you have separation here as well. But the main one to reverse somehow is to see whether it's reversible. This one, and it's again related to, well, it's not related. It is related, but I mean, it's just a little bit empty word saying that, to cone embedding, right? If you can find some graphs that you cannot revert these, right? Yeah, maybe. So that's a combinatorial, let's say, way maybe to look at that, perhaps. Although it's probably quite complicated, of course. All right. So in the remaining 23 minutes, 24 almost, I want to move to quantum graphs. Well, this is the start of lecture 4, if you wish, and it will be from through the way quantum graphs arise in zero-error quantum information theory. How do graphs arise from classical zero-error information theory? In the following way. So first of all, classical case. You have a noisy classical channel that has a certain alphabet here, and you want to transmit messages to, so this is from Alice to Bob, let's say, but it's a noisy channel, so you do not have perfect transmission, right? So you may have things like that, right? Every letter can be received as more than one output with certain probabilities, each one of them. So this boils down to, of course, certain conditional probability distributions for every x. You have likelihoods to be sent to A. This gives rise to, so the task here, the information task, is to transmit a message with zero error, right? So you want somehow to select a code which will be just a subset of this alphabet in such a way that when the receiver receives the message, no matter which one it was sent to, right, at the end of the day, he should be able to recover what she said without an error, perfectly. So now look at that, and you see that a zero-error code here will be just an independent set for a certain graph associated with the channel. And the graph here is the so-called co-feasibility graph defined by Shannon, and the underlying graph I will have x adjacent to y if these two letters can be confused upon the receipt by Bob. In other words, if I can find some A such that both of those probabilities are strictly positive. Right, very well. So then the independent set for G is the same thing as a zero error code for the channel. Let me give a name, noisy channel N. Therefore, the one-shot zero-error capacity is the independence number of G. So alpha of G, this is standard notation. This is the largest, the size of a largest independent set in your graph. This will be the maximum, that the optimal that you can do if you're given this task. Right? So independence number of G is the same as one-shot zero-error capacity. Of the channel N. This is the one shot when you apply the channel once, and as always kind of in information theory, you want to apply a channel more and more. So if you apply the channel twice, like that, the corresponding confusibility graph, so now I have a notation for the channel, so let me give the dependence on the channel of the graph. So the corresponding confusibility graph will be just the strong product of the same graph, and the strong product here is on vertices that are pairs of vertices. So these are the new vertices of the strong product, and two of them will be, say, x1, y1 will be adjacent or equal to x2, y2, precisely when each one of those conditions happens for each coordinate. All right, so then if you want to study the not one shot but just zero error capacity, what you do is you iterate like that, you compute independence numbers of these iterations of the graph, you normalize, take the nth root of those, and you take this to the limit.
So x1 is the...
I have made a mistake here, right? Thank you. Thanks very much. So, right. And this is quite hard to compute in general.
Take nth root of what?
Sorry, say again?
Nth root of what?
Right. So I will write this down. So you're taking the n-fold strong product of the graph, and then you're taking an nth root of that to normalize, and you're taking a limit as n tends to infinity. And this is what's called the one-shot zero error capacity of the channel or of the graph C0, C0 of G. So trying to understand what is C0 of G is a very hard problem. It's computed, unfortunately, for very few graphs. It is known. For example, for the odd cycles, it is not known apart from above 5. Above 5, it is not known. And the odd cycle is a very natural channel, right? The odd cycles, or cycles in general, they arise just by one letter can be sent either to itself or to the neighboring one. So, for example, suppose that you're typing on a typewriter, which on a computer, if you wish, a keyboard, you can confuse. That's an easy thing to confuse, right? The next letter. Right. All right. So now moving to quantum. So I have two choices: either to move to quantum now, or actually to give you, yes, maybe actually yes. Maybe what I will do is I will show how entanglement can assist in zero error communication first. So entanglement assisted. Entanglement assisted zero error capacities. Here again, the channels are classical, but the sender and the receiver share an entangled state, so they can use this entangled state to produce the final outcome. So here the picture is something like that. So here is my channel. This is N. So this is kind of the diagram of Shannon. First, I take a message. I encode it as an input of my channel. Afterwards, I apply my channel. I get some output. And afterwards, I decode the message. And what you want is, ideally, for kind of zero-error transmission, you want the original message to be equal to the decoded message. This is my my channel N, and then Alice and Bob. This is Alice. This is Bob. Sharing some entangled state means that they have, so this encoding process here is not deterministic, but it's obtained by through certain measurements on some part of Alice's entangled state. And similarly, the decoding is also obtained as a result of a measurement. So in other words, you will have some POVMs here associated with, this is over X, associated on the Alice side, this is the original message, and you will have some POVMs over here. This will be associated with the output. This will be obtained, so you want, in the simplest case where they just finite dimensional. In fact, the higher values, they are not investigated, so that's a nice kind of open direction if you wish, right? So you measure some C like that, and you want that, you have here that Y is the outcome of X, right? And you want this to be 0 if M is different from R. You want to receive the same M as it started. So more formally, you have a simulator starting with an N. So this is a kind of super channel, I think it's called. So you have inputs channels and output channels, right? So what you have is a simulator gamma. Maybe I will write the. All right. So here is X goes to Y. Here is M goes to M. You start with the original channel N. You want to simulate the identity channel here through some simulator gamma. Gamma is there for a correlation. You want this to be the output channel, so it's a correlation going that way. So gamma is nothing else but a certain correlation gamma of, you need to start with, so you want to obtain, you need to start with an M here, obtain an X, then put it in the channel, get a Y, and then spit out an R. So this is your correlation. No signaling correlation of your preferred type. Given such a no signaling correlation on this letter, so let me write it even more precisely, this will be on M cross Y going to X cross M. But this picture is kind of more useful to keep in mind. What is the produced channel? So this gamma gives rise to a map that you have an input channel N, classical channel on the first line, X goes to Y, and it can produce an output channel from M goes to M. Let me call it gamma of N. What is the output channel? Gamma of N. I need to tell you what is, if I'm given M, what I get for R. This will be, first I need to use my gamma. I'm having a certain input M, I want to get an R. Using the gamma correlation, from M I can get an X. Using the classical channel, from X I can get a Y. Given X, I have some Y. And using again gamma from 1, I can get to R. This expression gives me a classical channel, or any no signaling correlation gamma. And now you can insist that gamma is of a certain type. When gamma is of type Q, quantum type, this is exactly what's happening here in this diagram. And then in that case, this is the formal statement of what it means that Alice and Bob share this entangled state. They make measurements to encode and to decode. and they use the channel in between to send the encoded message into the pre-decoded message. And then you want to ask the same question. So what is the maximal way that you can do? So the aim here is to obtain the identity channel. You want this to be the perfect channel. The identity channel on M. So you're asking what is the maximum of the cardinality of M such that gamma of my channel N is fixed, given is equal to the identity on M for some gamma. Well, there exists a gamma, more precisely here, in say CQ class. Let's start with let's just consider the Q class. All right, so this we'll call alpha sub Q of my G. Depends on G. These are all non-negative numbers, so it just depends on the support of G. So therefore on the graph of G. Doesn't depend on the actual probabilities. The actual values of the probabilities here.
So you suddenly introduced G.
G is my graph of N. So this is G of N. So what matters is the graph. So actually the graph is the underlying thing. So this N, this channel N gives me a convisibility graph G. And if I try to compute this, it just depends. This relation here depends only on the support of N. In other words, it only depends on the graph of N and not on the probabilities, or not the actual values.
So shall we think about M somehow being small compared to the size of X and Y? Or?
It depends. It all depends on what N is, what the graph is, right?
But in general, it's kind of M should be smaller, right?
If you wish, yes, somehow, because so it's small in some sense small. But it's very rarely trivial, right? Trivial means that everything here can be confused, which is kind of a very unlucky situation, right? Yeah. So yeah, in principle, it's something small. In principle, yes, it is perhaps something small, but this is bigger. This alpha Q is bigger than the usual. So let me write G for Gn. This is less than or equal to this. And this is the entanglement-assisted zero-error capacity of my channel. It can be strictly bigger than alpha in general. How does it relate to the independence number obtained through the non-local games paradigm? You can just have the graph isomorphism game from the empty graph into the graph G. This will give you a quantum version of the independence number. So this is an open question, and maybe it's good to. I have already. That's good. I have a board here. So let's see now which one is. So the inequalities go like that. So the classical one is smaller than the one that is obtained through the game, the empty graph on some vertices is homomorphic into G. Well, it is a little bit, yeah, it's not exactly that, right? What I want is really, for the independence game, I want the full graph to be embedded into the complement of G. That's the right thing. And this will be less than or equal to this entanglement-assisted one-shot zero-error capacity. So this inequality, whether this is equality or not, we do not. I don't think it's known. So do we have equality? It's a kind of a curious problem at all. That kind of it's a curious thing. There is some reason, kind of that probably I don't know. At least I don't understand that kind of. These should be at all related in some sense. right? So there is some computation needed for that inequality. One of them arises from, these two parameters arise from a completely different way somehow, right? One of them is smaller than the other. So I have 4 minutes, which I will use. So what I want to do is now I want to move to the quantum case. So let me use these 4 minutes to say how do we move from classical to quantum generally, right? So in that case, you would have you want to have now a quantum channel, and in that case, it will be from matrices over X to matrices over Y. And you want to transmit quantum information with 0 error. Now, looking back at what it means in the classical case, transmitting with 0 error means that I was able to find, so this is just the motivation, why is this kind of the right definition? So classically, I was able to find these specific letters of the alphabet, such that when I push them through with the channel, so this is just my EX start, right? This is just the state, diagonal state, corresponding to this X. They're all orthogonal when I view them at the output. So they are perfectly distinguishable. That's why the receiver can identify which X has been sent. So now this is quantizable easily. I want now a certain set of orthogonal states. A 0 error code for my quantum channel phi consists of some orthogonal states, and because they're orthogonal, I can just pass to a pure state, in fact, something that's supported on the same support. So this will be just a collection of pure states, C1 start, up to Cm start. These are unit vectors, the Xi are unit vectors. These are the corresponding rank 1 projections. So these are pure states in Mx, such that when I pass them through the channel phi, I will have perfect distinguishability. They will be disjoint, they will have disjoint supports. I want Ci start after the application of phi to be orthogonal to phi applied to Cj star for every I different from j. And now you remember the Krauss decomposition. Krauss decomposition tells me that phi has the following form. If I have a state rho, it will be the sum of some operators ai, rho, ai start, some length here, such that they will have the property that ai start, ai is equal to the identity. Now I sit down and compute what this means, and turns out that something really nice. So it's equivalent to the following: ai start, aj has to be orthogonal to I. So let me use a different. Oh, that's okay. AI start. Aj has to be, if I play with some Cp and Cq here, this has to be 0 if P is different from Q. Now we take a look for all I and j. Take a look at the span, in other words, of those operators. So let me call it S sub phi. It depends on phi. So I and j are from 1 to d. I say it depends on phi. A priori depends on the Krauss representation here, but it doesn't at the end of the day. So it's just the attribute of phi, not of the Krauss representation. So you want these vectors to be orthogonal, right? So you want such orthogonalities. Now, what is nice about this S-phi? It's an operator system. So S-phi is an operator system in M sub x. This is the version of the confusability graph of the channel. Why? Because if you start with the classical, and this is where I will finish. I will take 10 seconds if that's okay. So if you have a classical channel, you have a corresponding confusability graph. And if you represent your classical channel in some cross representation, you will arrive at some kind of operator system. And this operator system is exactly S sub G, so this will be exactly S sub n, which is by definition equal to the span of those matrix units Ex, Ey start, which are adjacent or equal in the graph G. So it's a graph operator system, let's call it. So it's associated with the graph. And if you have a classical n, you arrive at operator system that arises from a classical graph. So that's why operator systems that are not necessarily graph operator systems can be thought of, a candidate at least, for quantum graphs. These are easily characterizable. These are precisely the ones, the operator systems that are bimodules over the diagonal massa in the matrix. Okay, so I'll stop here. Thank you.
Thank you. Are there any questions?
So when you write alpha compared to alpha q squiggle, so now we are once again talking about the one-shot zero-error capacity, right?
Only one shot. Yeah, exactly. So that was just a flavor of what is the kind of the non-one shot, but yeah.
And if I have to think about like the C0, does this increase if n goes to infinity? Like
Yes. So that will be this will be an increasing sequence. Yes, it will be an increasing sequence.
And do we know that even if you would look at C0 of G, alpha Q is still larger?
No, we do not know that. In general, how it increases, it's kind of also not very well understood. So we know that it can increase. We know that it can increase. I believe we know that it can increase kind of arbitrarily long, but examples of where it increases all the time, I don't think there are known. So in general, yeah, I mean, there's this area of kind of zero-error quantum information and information theory. There are some results. I mean, you look, but I mean, in general, many things are not known.
Yeah.
Yeah.
I guess the reason I'm asking, in a sense, if you know that alpha Q of G is strictly bigger than even C0 of G, then it's really like...
Right. You want to compare the classical one-shot, the classical zero-error capacity with the quantum one-shot zero-error capacity. I see. I don't know. I'm not sure. I'm not sure whether there are results in there. I don't know.
Are there any further questions?
Yeah, so somewhere you mentioned quantum chromatic numbers. So can you say something more on that?
Yes, so there are examples there, and it's the Adamar graph that gives you examples. So there are several examples. The original one was based on the Adamar graph. Adamar graph of so over there the vertices are plus minus vectors, plus minus 1 vectors. And the relation is two of those are adjacent if the product is 0, the inner product is 0. That's the adjacency relation, and there is a nice computation. So it uses this separation uses a combinatorial result that the chromatic number of the Adamar graph is almost exponential. It's exponential, really, somehow on n, on this n. Yeah, right? But the quantum one kind of turns out to be exactly equal to n. So actually, this separation is not only just a separation; it's a very strong kind of separation between the two. Just the order of their growth is completely different. And it needs a computation that, actually I will go back to this. It needs a computation that involves unitary basis, and that will be kind of, I will talk about it in the last lecture, unitary basis of kind of what's called super dense coding. Unitary basis of matrices, so matrix spaces that have unitary basis. So they are always like that, basis like that. One way to see it is you take the shift, raise it to some powers, you take the diagonal that consists of some powers of some root of unity, nth root of unity. Take the product of those, and this will give you kind of, this is what behind the computation of the quantum chromatic number of this.
Last questions? If that's not the case, then we'll have a coffee break now until 11:15, but before that, let's thank Gemma.